Our lesson on 3.4 for Trig discusses arc length and area of a sector. So our formulas are going to be very important. We've actually talked about this formula before in, I think it was section 3.2, where the central angle is our arc length divided by the radius. And remember, that stems off of the circumference formula. Now if you take that equation and you rearrange it by solving for the s, so you multiply both sides by r, you'd end up with the formula s equals r times theta. So that is the formula that we're going to refer to when we ask you for arc length. And remember, theta is always a measurement in radians. Your angle must be in radians. So give the length of the arc cut off by a central angle of 2 radians. So there is your theta. And the radius of 4.3 inches. There is your r. So our arc length is 2 times 4.3, which gives us 8.6, and then labels are very important in this section, inches. Our Ferris wheel problem, this is called George's Ferris wheel. Recall that the diameter is 250 feet, so what that means for us is that the radius would be 125 feet. So I'm going to mark that down right now. And theta is a central angle formed as the rider travels along, and the initial position is called p sub naught, and the new position is p sub 1. Find the distance traveled by the rider for these two different central angles. So we're going to do two problems, and they're both arc length problems. And the first one, if theta is 45 degrees, remember when you use the arc length formula, it's radius times your central angle in radians. So you would have to convert 45 degrees to radians by multiplying it by pi over 180. Now I would accept an answer that's not decimals, one where you leave it in terms of pi, but for the problem itself, it really makes more sense to write your answer as decimals. So 98.2 feet is when the rider went 45 degrees, and similar problem, this time the rider is traveling 105 degrees. So we're going to multiply it by pi over 180, and again decimals make more sense for what we're doing here. 229.1 feet. You'll notice that if you check your homework in the binder, I left a lot of my answers in terms of pi simply because when I was making my key I didn't have a calculator, so it was easier for me to leave them in terms of pi. So we have a clock, and the minute hand of the clock is 1.2 centimeters long. We're going to use that as our radius in this problem. To 2 sig figs, how far does the tip of the minute hand move in 20 minutes? So first I want you to think about a clock. 20 minutes is a third of a rotation because it's 20 out of 60. Now we're going to have to take that fraction and multiply it by 2 pi radians to figure out how many radians it's actually rotated. So if you convert that and leave it in terms of pi, it's 2 pi over 3 radians. So that is my central angle. So arc length is our radius times our central angle, which in our case is 2 pi over 3. And on your calculator, if you want a decimal, it comes out to 2.5 centimeters. Okay, so this example is talking about there's an airplane up here in the picture, and the person's standing on the ground and notices that a 747 jumbo jet subtends an angle of 0.45 degrees. Now that means that if they were using some sort of a surveyor's device, if you were to look at the beginning to the end of the plane, that was a 0.45 degree angle. So the length of the jet is 230 feet. They want to know how far away the jet is, meaning the altitude. So that would end up being the radius, because if you thought of this as being a gigantic circle, they want us to find radius. So if I take my arc length formula and I solve for r, that would be arc length divided by theta. So arc length is the length of the plane, actually, 230, divided by, now be careful, it's the angle is 0.45 degrees, but we need it in radians, so it's times pi over 180 in parentheses. So you can type that all in one step on your calculator. And it says to the nearest 1,000 feet, so it's roughly 29,284.5. So when I round that to how they wanted it, it ended up being 29,000 feet. This was not a super accurate measurement because the plane is obviously not an arc, but it's an estimate. Next, where I have a formula for the area of a sector, that would be like if I took a piece of the pie out and I want to find the whole area instead of just the arc length. So this is the formula for area of a sector, 1/2 times radius squared times theta, and again, your central angle has to be in radians. So our first example, find the area of a sector. The central angle is 1.4 radians and the radius is 2.1. So this is really just a plug and chug problem. 2.1 squared, and then the central angle is already in radians, so it's just 1.4. So on my calculator, I think that comes out to roughly 3.1, and then label this meters squared because it's area. Example 6. This time we've got a central angle of 15 degrees, and this is kind of unique. The area is given to you. So when I think about my area formula, I gotta be careful where I plug things in. So the area is pi over 3. We have 1/2. I don't know the radius. And then careful again, my central angle is not given to me in radians, so I would have to convert that to radians. So when I simplify that a little bit, let's see. I think I end up with, well, that's pi over 12. So I got pi over 3 equals 1/2 r squared times pi over 12. To get rid of the 2 and the 12, I'm just going to multiply both sides by a 24. So that'll cancel out with those, but then I have to do it over here as well. So 24 over pi over 3, let's see, that's 8 pi. Oh, no it's not, because this pi is going to cancel as well. Let's back up a second. This pi and this pi will end up canceling. So all I have is 8 equals r squared. Now when you square root both sides, you get radius as 2 square roots of 2, and then we have to label this. Since it was centimeters squared for the area, your radius is in centimeters. So, a lawn sprinkler located at the corner of a yard rotates 90 degrees. So if there's your sprinkler, he's going to rotate 90 degrees, oops, and he's going to cover this whole sector with water. And it projects out 30 feet. So that looks like our radius. And remember, theta is has to be in radians. So when I go to find the area, 1/2, and then r squared. And 90 degrees I know is pi over 2, so I'm just going to write that as pi over 2. So if you wanted a decimal on your calculator, that would probably be most appropriate. Looks like it's 707, and because it was feet for the radius, our area is feet squared. And that is the first part of your lesson. I believe there's another worksheet on 3.4. And I don't know if I have a presentation ready for it, but it basically runs along the same concepts.